Hi guys, good morning.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Good morning.
Good morning, sir.
Good morning,
Good
sir.
morning, guys. This is
Morning.
Good morning, sir.
morning. Good morning. Great to see. Not really see, but great to have you guys in the session. This is our first class. Till now, you were studying probability, and Professor Madhukan Sharma was leading the lectures. For the rest of the semester, I'll be teaching you guys statistics and information theory. So the second half of the course is about statistics and information theory. Uh, but before we start, I'm just curious to know how many of you are looking forward to coming back on the campus. Okay, I can see a lot of hand raises. I can't really count that. So let me just do a quick poll. Are you able to see the poll?
Yes,
Yes,
sir.
sir.
Yes, sir.
Oh, there is only one no. Wow, this is awesome. Great, great, great. Super, super great. Happy to see that most of you are planning to come to campus. There is only one student who has said no so far, and three who have said not yet decided. Closing the poll now. Okay. So are you, let me see if I can show you the, are you able to see the results on your screen or no?
Yes, sir.
Yes, sir.
Okay. Good, good, good. Okay. One second. There's some people in the meeting room. Okay. Please be on time. I've let you in right now, but I'm closing the meeting room now. If people join now, they'll not be able to enter. Okay. So let's start. Um, if you have a question or something, then please raise your hand and speak. I am not able to see the chat. Okay. Are you able to see the screen? Is it visible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Thank you. So we're going to do two topics. One is statistics, and the other topic is information theory. So for statistics, the book that we will be following is um, called Introductory Statistics by Sheldon Ross. Um, I'll be following the third edition. But even if you have the second edition, that's also fine. Information theory, we will be following the book called Elements of Information Theory by Thomas and Cover, the two authors. I'll be following the second edition for this. And second edition is quite old. I think second edition itself is about 10 years old. So you should be able to get it without much difficulty. Okay. So these are two topics that we will be covering. So we will start with the topic called distributions of sampling statistics. This is chapter 7 of the textbook. So by textbook, I mean, this case, introductory statistics. So the first six chapters are a lot to do with probability theory. I believe you already know random variables, you already know continuous random variables, discrete random variables, normal distribution, and I think you have also done uh, Chebyshev's inequality, Markov's inequality, weak law of large numbers, and strong law of large numbers. So in the first 1 or 2 lectures, there might be some repetition. I'm not sure, but the rest of it should definitely be quite different. But you definitely need to know random variables. So even today, the examples that we will look at, you will need to know what is a random variable, what is the probability distribution, how do you compute the expectation, how do you compute the variance. So these topics you really need to uh, revise if you have forgotten it. Okay, so let's start with an example. Let's say you have a roulette table. Anybody knows how many slots are there in a roulette table? Nobody has been to last lecture. How many? There are 38 slots. So it starts with 0, then there is 0, and then from 1 to 36. And let's say you bet $1 on a number. So what is the, how much do you lose and how much do you win? So if you lose $1. So what you lose is $1. And what is the probability of a loss? And if you win, how much do you win and what is the probability of this? So loss is obvious. You put $1 in. If your number doesn't come, then you lose $1. What is the probability of you losing?
37 by 38.
Yes. So if you are uh, choosing one number and that number is not coming out of 38 numbers, there are 37 which are unfavorable to you. So the probability of losing is 37 by 38. What do you win? Anybody knows? If suppose your number comes, then how much do you win?
$10.
No, you win
37.
35. No, it's not 37. That would have been great. So casinos are not, they don't believe in fairness, to put it this way. If you've seen that movie called Oceans, how much was it? I think 11 was the first one. There's a very popular dialogue by Danny Ocean that the house always wins. So they don't give you $37. When you win, they don't give you $37, they give you $35. And the probability of winning is obviously 1 by 38. So the reason I say it's not fair, so what do you mean by fairness? So fairness means in the context of probability and in the context of gambling. Yeah, Achyut, if you have to say something, then say it. So now fairness means that expected value of win is 0 or loss is 0. So in this case, what is the expected gain? In this example, what is the expected gain?
minus 2 by 38?
Yes, exactly. So it is minus 1 multiplied with 37 by 38 plus 35 multiplied with 1 by 38. And this comes out to be minus 2 by 38. So we would have said that it is a fair place. It is fair if this value was equal to 0. But this is not equal to 0. So this is actually equal to minus 5.3 cents. So what it means is that on an average, you are going to lose uh, a little more than 5 cents every time you're placing a bet of $1. So if the winning amount was, if suppose this was 37, then this would have been 37 and this would have been 0. So if it were a fair place, then they would have given you $37 in the win, and then it would have been minus 1 into 37 by 38 plus 37 times 1 by 38, which would have been 0. That would have been a fair game, but it's not a fair place. So on an average, the expected gain on the bet is minus 5.3 cents. And what we are going to see, one of the exercises that we will do later in the course is so in this example, you saw that the probability of winning is 1 by 38. It's a small number. It's about 2.5%, little more than that. But what we will see is that what happens if you play repeatedly. Let's say you place one bet, you lose or you win, that's fine. Let's say you place 10 bets back to back. Let's say you place 1,000 bets. Let's say you place 10,000 bets. You keep betting one after another, one after another, one after another. What happens in the long run? That is one of the inquiries that we want to have. Uh, that people tend to believe, okay, I lost this time, maybe bad luck. Let me try again. Let me try again. Let me try again. So we want to see mathematically what happens when you do it. What is the end result? Do you end up winning something or do you end up losing? So that is one of the things that we will investigate in this course. In fact, in this particular chapter. Okay, so to build up all of that, to be able to study this in more detail, we want to do a lot of definitions. So the first definition that we are going to do is that of a sample. So what is a sample? So if x1, x2, xn are independent random variables, having a common probability distribution, we say that they constitute a sample from that distribution. And sampling is everywhere. Just now we had elections in a few states, so they do sampling when the canvassing is going on. They talk to people. They obviously cannot talk to all the people. They cannot talk to all the people who are going to vote. Then there is this exit poll, which is very famous. You talk to people who are coming out of the polling booth, and then you ask them whom they voted for. That is a sample. Okay. Uh, so the real population is all the people who voted, but sample is all the people one spoke with who are coming out of the electoral booth. Then there is, you could say you want to compute average height of an Indian male. So you can't go around measuring height of 20 crore people. You probably take 100 people in every big city and you compute their height and you take an average of that. That is a sample. So what are the important characteristics? The most important characteristic is that they are independent random variables. So x1, x2, xn are independent random variables and they have a common probability distribution. So we assume that the probability distribution for all the items in a sample is the same and that all these random variables are independent of each other. So if that is the case, then we say that they constitute a sample from that particular distribution. So just to put it to just look at it visually, let's say this is the whole population. These are this is the entire population, and you pick some samples from here. So the red dots are the sample. Okay, and then we will define some characteristics. We will define population mean, which is mu, population variance, which is sigma square, and we will define these characteristics for a sample. We will define sample mean and sample variance. And so this is where you want to be really careful with the notation, so that uh, sample mean we will always represent by x bar, and sample standard deviation we will usually write it as s square. So this is where you want to be careful. This is mu, population mean, population variance is sigma square, sample mean is x bar, and sample variance is s square. So what is population mean, or what is sample mean? So let's say let x1 to xn be a sample of values from this population. Then x bar is defined as x1 plus x2 plus xn divided by n. So let's say I take all the students in this class and I total their marks and I divide it by the number of students in the class. That is how I get the sample mean of all the students who are studying probability and statistics. Okay. So this will change. The point to note here is that the value of the sample mean x bar is determined by the values of the sample. So if suppose you're trying to compute, let's say, average height of adult male, then the value will differ depending upon which sample you take. So what we're trying to say is that x bar itself is a random variable. X bar itself is a random variable. So this is to be contrasted with mu and sigma square. So mu is not a random variable. When you have a population and you have a population mean, then mu is not a random variable. When you have a population variance sigma square is not a random variable. These are numbers. These are not random variables. However, the value of the sample mean x bar, this will depend upon what sample you have taken. So if you take this sample, these 7 entries, then you will get a different sample mean. If you take these 7 values, you'll get a different sample mean. If you get these 5 values, then you get a different sample mean. So the sample mean x bar will depend upon what values you are picking. What is the value of the random variables x1 to xn? Similarly, sample variance also, S square is also a random variable because it will depend upon what values you are picking, what sample you are choosing. So this is a very important distinction that you need to keep in mind, that x bar and s square are themselves random variables, wherein mu and sigma square are numbers. They are not random variables. So x bar, so the value of the sample mean is determined by the value of the random variables in the sample. Hence, x bar itself is a random variable. And if x bar itself is a random variable, then we can compute statistics on x bar. So we can talk about things like E of x bar and variance of x bar. We can talk about these things. We can talk about what is the expected value of the x bar and what is the variance of x bar. Why? Because x bar itself is a random variable. And we'll do the proof later. So proof later. But right now, I'm just stating it without proof, that expected value of x bar turns out to be mu, and expected value of variance of x bar turns out to be sigma square by n. What is n here? N is the sample size. So just to recap what we have said there's a whole huge population, and you want to compute some statistics on the population. You cannot collect data on the whole population. It is too much work. So you take a sample from the population. Now the sample would differ. Let's say if we talk about election, then depending on which news channel you're talking about, one news channel will go to a particular set of people, another news channel will go to a different set of people. So all the news channels will choose a different sample. So uh, so so the x bar, x1 to xn that they choose are different, and hence the mean that they get, x bar itself is different. So what we are saying is that x bar itself is a random variable, and if it is a random variable, then we can talk about its mean and we can talk about its variance. So it turns out that mean of x bar is the same as mu, which is the population mean. So this is the population mean. But we get a more interesting result for the variance. The variance of the sample. Variance of the sample is, so this is what sigma square is what? So sigma square is population variance. So what we are saying is that the variance of x bar is variance of the population divided by the size of the sample. So what it means in particular is that variance goes down as sample size increases. When you take bigger and bigger and bigger sample, then the variance of x bar, variance of the sample mean, that keeps going down. And that kind of makes sense. Let's say you're talking about elections in a state like UP, which probably has, I don't know, maybe 10 crore voters are there. If you talk to 10 people only, then you'll get a certain X bar. But it is understandable that the variance will be high. But if you talk to 10,000 people, then it is obvious that you will get a lower variance in your population, in your sample mean. So in terms of for random variable, normal random variable, this is how it looks. So let's say if you were to plot the graph for, they're all normal random variable. So if suppose you take a sample of size 1, okay, and so what we are plotting here is uh, densities of sample means. From a standard uh, standard normal population N01, mean is 0, variance is 1. So if we were to do that, let's say we take a sample of size 1, then it'll look like this. This for n equal to 1. But if you were to take n equal to 2, it'll look like, my drawing is not so good, but let me just try. It'll basically be narrower and higher. This is for n equal to 2. And let's say we do it for n equal to 4. Then n equal to 10. So what we're trying to show here is that as you keep increasing the sample size, as you have bigger and bigger sample size, then the density function becomes narrower and narrower. It, it comes closer and closer to that. So the distribution becomes closer and closer to the mean value. So the variance decreases. What these graphs are essentially showing is that the variance is going down as the value of n is increasing. N is the sample size. So let's look at a smaller example. Let's look at an easier example. In fact, let's look at a discrete example. So let's say we take a sample of size 2. Let's say the random variable x can take two values. It can take value 1 or it can take value 2. Probability of taking value 1 is half. So let's say it's a coin. Okay, it's a coin flip. You say head is 1, you say tail is 2. Probability of getting a 1 is half. Probability of getting a tail is 2. Okay, so that is the setup. Now, probability of x equal to 1 is half. Probability of x equal to 2 is half. Okay, so x can take two values, either 1 or 2. Now, what is mu and what is sigma square? This example. So what is mu and what is sigma square?
Three by two mu
Yeah,
and sigma square 1/4.
so mu is 1 into 1 by 2 plus 2 into 1 by 2. So it takes value 1 with probability half and value 2 with probability half. So this is 3 by 2. How do you compute sigma square? Sigma square is expected value of x minus mu whole square. So it's 1 minus 3 by 2, which is half, 1 by 4 to 1 by 2 plus 1 by 4 into 1 by 2, that is 1 by 4. So you get mu and sigma square. So mu is 3 by 2 and sigma square is 1 by 4. So this is the random variable that we're talking about. We have not done any sampling till now. Okay. Let's say we take a sample. We take a sample. Consider a sample of size 2. Okay. So you're doing this twice. So you have two values, x1 and x2. Now, what are the possible values that x1 and x2 can take? What are the possible values that x1 and x2 can take? Both can be 1. X1 can be 1, x2 to be 2. You're taking a sample of size 2. It's possible that both the values in the sample are equal to 1. 1 is 1, the first is 1, second is 2. This is 1, this is 2. Or both are equal to 2. These are the possibilities. Yeah. And what is the probability for each of these events? So this is half into half, 1 by 4. All are 1 by 4. Yeah. When you take a sample of size 2 in this population, each value could be either 1 or 2. So it's possible that both of them are equal to 1. That probability is 1 by 4. It's possible that x1 is 1, x2 is 2. This probability is 1 by 4. It's possible that x1 is 2 and x2 is 1. this probability is 1 by 4. And it's possible that both of them are 2 and the probability is 1 by 4. Now, what is X bar? What is X bar? We said that X bar itself is a random variable. Yeah, somebody was speaking.
Different for all 4 values.
Let's say it louder.
Different for all the 4 values.
Yes. So X bar itself is a random variable. So it is a random variable whose value is dependent on the values of x1 and x2, right? So X bar can take what values? So if you look at this, X bar in this example is what? So if we can write it here, actually it's better. What is X bar here? So X bar here is 1 plus 1 by 2, which is 1. X bar here is 1 plus 2 by 2, which is 1.5. Here it is 2 plus 1 by 2, it is 1.5. Here it's 2 plus 2 by 2, which is 2. So X bar is taking these 4 values. It is taking value 1 with probability 1 by 4. It's taking value 1.5 with probability half. And it is taking value 2 with probability 1 by 4. So these are the values and probabilities for X bar. It's taking value 1 with 1 by 4, 1.5 with probability half, and 2 with probability 1 by 4. So now we can ask the question, what is the expected value of X bar? So what is the expected value of X bar? Expected value of X bar then is 1 into 1 by 4 plus 1.5 into 1 by 2 plus 2 into 1 by 4. And when we do this, we get 3 by 2. So this is just to verify what we said earlier, that expected value of X bar is the same as mu. So this is the same as mu. It is the population mean. Any questions up to here?
Sir, I just wanted to confirm that the two values that we are talking of 1 or 2, was that the set of all possibilities?
Can you please repeat? Are you talking about this page?
No, sir. The previous page, the two values 1 or 2 that we are talking of.
Over
Is
here?
it, yes, sir. Is it the set of all the possibilities?
Yes. This is the set of all the possibilities for X.
Okay, okay, sir.
Okay. So think of it like this, that let's say in your class, I ask every student to choose a number, and every student chooses either 1 or 2 with equal probability. So all of you toss a coin, and if you get a head, you choose 1. If you get a tail, you choose 2. And then out of the whole class, right now, how many people are there? So right now there are 200 and, oh, it's interesting. There are exactly 2 to 2 people in the class. And this is SC2 to 2. Okay, so out of 222 people, I choose 2 people randomly. So that's what we are doing here. We're choosing a sample of size 2. So out of 222 people, we choose 2 people at random. Okay, so let's say Tarang and Bhavya. And then we ask, what did you choose? Now, it's possible that both of them chose 1 1. Possible that Tarang chose 1 and Bhavya chose 2. Or Tarang chose 2 and Bhavya chose 1. Or both of them selected 2. So these are 4 possibilities. Probability of each one of them is 1 by 4. Now, in these 2 possibilities, the answer is the same. Answer for X bar is the same. Whether Tarang chooses 1 and Bhavya chooses 2, or whether Tarang chooses 2 and Bhavya chooses 1, in both the cases, the mean is 1.5. X bar is 1.5. So we combine these two. So we say that when X bar is 1.5 with probability half, it's 1 with probability 1 by 4, and it's 2 with probability 1 by 4. And so X bar itself is a random variable. So what we are saying in this slide is that X bar itself is a random variable. It can take these three possible values with three different probabilities, three distinct probabilities. So we can compute expected value of X bar. We are treating X bar as a random variable. We can compute its expected value. So we get this number, and it turns out to be the same as the expected value of the population. That is what we have said here.
Excuse me, sir. Can you please reshare your screen? Because from my end it's stuck on previous one.
Yes, sir. In my screen also it's free.
So you can't see this hello written. You're not able to see hello on the screen.
No, sir.
Yes.
Screen is free for.
Yes, sir. It
Oh.
is.
Okay, thanks for pointing it out. Let me try again. So in future also it may happen. WebEx is a very reliable software, and it happens. So when it happens, you let me know as soon as possible so that we waste minimum time. Are you able to now see this hello written in red?
Yes.
Yes, sir.
Yes, sir.
Okay.
Sir,
Yeah.
sir, as we have talked about expectation and variance of x bar, we can also talk about expectation and variance of s square, that is sample mean and sample variance.
Yeah, we could do that.
As sample variance is also means random variable.
Of course, sample variance is also a random variable because it is a function of the sample that we have chosen.
Okay, sir.
Right.
Thank you.
Yeah. So this example is not complete. We are still doing this example, but what you have said is valid, and it will come in future. Okay. So what we did till now is that we computed the expected value of X bar, and we saw that it is equal to the expected value of the population, which is 1.5. Now we want to also verify what is the variance of X bar. Ouch. What is the variance of X bar? So variance of X bar, we know X bar is a random variable. So its mean is 1.5, and we know the probability function, so we can compute its variance. So it's expected value of X bar minus mu whole square. So it's 1 minus 1.5 whole square into 1 by 4 plus 1.5 minus 1.5 whole square into 1 by 2 plus 2 minus 1.5 whole square into 1 by 4. Yeah. And this is 0, the second term. This is 1 by 4 to 1 by 4 plus 1 by 4 into 1 by 4. So that is 1 by 8. And this turns out to be equal to basically 1 by 4 divided by 2. And what is 1 by 4? 1 by 4 is sigma square. So this is equal to sigma square by n is variance of X bar. So this is what we stated earlier, that variance of X bar turns out to be sigma square by n, and in this example is 2. So
Excuse me.
sigma square was 1
Yes,
by
sir.
4. Yeah.
Sir, screen froze again for
sir.
my end. The screen froze again.
Yes, sir.
Is it for everybody? Like nobody can see
Sir.
the.
Sir, I think, sir, could you unlock the meet so that we can like try to rejoin so that I think then the
Yes, sir.
issue can like
Yes,
resolve.
let's try that. I've unlocked. But is there anybody who can see it, or is it frozen for everybody? That's what I want to know.
No, sir, we can see it perfectly.
From
Sir,
my
it's
concern,
perfectly
Yes, sir.
visible.
You can see this X in red and in a circle. You can see it right now.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. Yeah. So please disconnect and rejoin. Um, yeah. So what we are showing here, we computed variance of x bar. It turns out to be 1/8. So it's essentially 1/4/2. And what is 1/4? 1/4 is sigma square. We computed that earlier. So what we have shown here. This is not a proof, by the way. This is just to show, just to verify that variance of x bar is equal to sigma square by n. So if you were to draw it, uh, let's say population probability mass function. So it takes two values, 1 and 2, and with probability half. So when as far as the population is concerned, it takes two values. It takes value 1 or it takes value 2 with probability half each. But when you talk about probability mass function of sample mean, then it can take three values. Sample mean can take three values. It can take value 1 uh, with probability 1/4. It can take value 1.5 with probability half, or it can take value 2 with again probability 1/4. These are three values it can take. Okay. Any questions till now?
वाड़ू बंद कर लो बच्चों में
Any questions up to this point?
No.
Okay, so what I want you to do is try it out for a sample of size 3. So to work this out, for a sample of size 3. Same example. Do it for sample of size 3. For sample of size 3, what you need to show is that expected value of x is the same as mu, which is 3/2, and you need to show that variance of x bar, sorry, expected value of x bar, and variance of x bar will be equal to sigma square by 3, which is 1/12. So try it out for sample of size 3. Okay. What I'm going to do is break you up into breakout sessions so that you can talk to each other. Wow, this is a big class. Let's say I break you into each session will have 4 to 5 people. Take support from each other, discuss with each other. You can set up group leader who will share the results when you come back to the main meeting. Before I do that, is there any question about what you need to do? Are you clear what you need to do?
Yes.
Okay, great. So did anybody try it out? Did anybody get the answer? Could you verify that expected value of x bar is indeed 3 by 2 and variance of x bar is indeed sigma square by 3, which is 1 by 12.
Yes, sir.
Yes, sir.
How,
Yes, sir.
how did you compute x bar?
By sum and by divide by 3.
So what are the possible values?
8 possible values.
1, 2, 4 by 3 and 5 by 3.
Okay, so the possible values of x bar are 1, 4 by 3, 5 by 3, and 2. Okay, and what are the probabilities?
1 by 8,
5, 3 by 8,
3
3
by
by
8, 3 by 8, 1 by
1
8.
by.
And when you do this computation, then you get expected value of x bar to be
3 by
3
8.
by
2. And now that you have the probability distribution, you can also compute its variance. Similarly, you can compute variance of x bar. So that will be 1 by 2 square into 1 by 8 plus 4 by 3 minus 3 by 2. So that is
1, 6.
1 by 6 square into 3 by 8 plus 1 by 6 square into 3 by 8 plus 1 by 2 square to 1 by 8. And you're saying that this turns out to be equal to 1 by 12, which is sigma square by 3. Yeah?
Yes, sir. Sir, hello?
Yeah?
Sir, I have a doubt. Let's say we take a sample of 1, 1, 1 of size equals to 3. So the x bar is coming out to be 3 by 2, not plus 3 by 3.
If you take a sample of, let me write it in a new page. What you're saying is you're taking x1, x2, x3, and x1 is 1, x2 is 1, x3 is 1. This is what you're saying?
Yeah, right. Then how do you compute the x bar? Like mine one is coming out to be 1.
So x bar is a summation of xi by n. So it is 1 plus 1 plus 1 by 3, which is 1.
Okay, I must have done. Sorry, sir.
Yeah, so here n is 3. In the previous example, n was 2 because we took a sample of size 2. In this example, we are taking a sample of size 3. So n is 3. So we divide by 3. So we get 1 as the x bar. Any other questions about this example? Okay, so I want you to try out one more exercise. So this is another exercise for you to completely understand or rather completely uh, test your understanding of what we have done. So in the previous example that we saw, we said that the probabilities are equal. You know, x1, and x2 can both take values 1 or 2 with equal probabilities. Now we are saying that the probabilities need not be equal. So let's say you take a sample of size 2 from a population. In the population, x can take value 1 with probability 0.7 and x can take value 2 with probability 0.3. Okay, so given all this, what you need to do is you need to compute E of x and let me just write it down more simply. Compute mu and sigma square. Uh, then you need to find out what are the possible values. Of x bar. What are the probabilities? For these values of x bar. So x bar is a random variable, so it can take certain values, and which with each of these values there is a certain probability assigned to it. So what are those probabilities for all the possible values that x bar can take? And then you compute E of x bar and variance of x bar. Okay, and what you want to verify is whether E of x bar is coming out to be the same as mu, and whether variance of x bar is coming out to be sigma square by n. That is what you want to verify. Okay. Any doubts about the statement of the exercise? What do you need to do? So starting the breakout sessions, try it out with each other and you come back and then you share. Hi, welcome back from the breakout sessions. So the problem was that there's a random variable x which takes two values. It takes value 1 with probability 0.7 and it takes value 2 with probability 0.3. So you can think of it like being a biased coin. So the probability of head is 0.7, probability of tail is 0.3. If you get a heads, then you choose assign number 1 to it, and if you get a tail, you assign number 2 to it. So the first part is compute mu and sigma square. What will be mu and sigma square?
1.3 and 0.21.
Yeah. So you compute mu as 1 into 0.7 plus 2 into 0.3. So that is 0.7 plus 0.6, which is 1.3. And sigma square is 1 minus 1.3 whole square into 0.7 plus 2 minus 1.3 whole square into 0.3. So that is 0.09 into 0.7 plus 0.49 into 0.3. So that is 0. Yeah, I'll just write down the final answer 0.21. So that is mu and sigma square. Now, what are the possible values of x bar? So what are the possible values that x bar can take? And what are their probabilities?
1, 1.5 and 2.
Yeah, so x bar is the same as before, or the possible values of x bar is the same as before. It can be 1, if both are 1, it can be 1.5, it can be 2. What is the probability that x bar is equal to 1? When will x bar be
0.49.
equal to 1?
0.14. 9.
Point?
49.
49.
Yeah, so one thing I just want to tell you, you never call it 49, okay? You don't say 0.49, you say 0.49. After the decimal, you don't say it like it is before the decimal. Yeah, so you get a value 1 with when both of them are equal to 1, 0.7 into 0.7, it is 0.49. When do you get 1.5?
0.42.
Yeah, so it is 0.7 into 0.3 into 2, so it is 0.42, and you get a 2 when both of them are equal to 2. This is equal to
0.09.
0.09. Okay, so now you want to compute what? Now you want to compute its expected value of x bar and variance of x bar. The expected value of x bar is 1 into 0.49 plus 1.5 into 0.42 plus 2 into 0.09, and it turns out to be equal to 1.3. Variance of x bar is 1 minus 1.5 whole square into 0.49 plus 1.5 minus 1.5 whole square into 0.42 plus 2 minus 1.5 whole square into 0.09. This requires some more work, but this turns out to be 0. Anybody got the answer for this?
0.105.
Yeah, and this is equal to 0.21 by 2. So this is sigma square by 2.
Sir,
Yeah.
sir, in the variance of x bar, there should be 1 minus 1.3 instead of 1 minus 1.5.
Yes. Yeah, I think I made a mistake in writing. Should be 1.3 everywhere. Thanks for being awake. One minus 1.3, 1 minus 1.3, 2 minus 1.3. Yeah. So 1 minus 1.3 whole square, 1.5 minus 1.3 whole square, and 2 minus 1.3 whole square. Why? Because expected value is 1.3. We're talking about expected value of x bar. Yeah, thanks for pointing it out. Okay. So so this completes this example. I'll just take a few more minutes and complete the proof, and then we will end the lecture for today. So the proof is pretty straightforward. So what is x bar? X bar is x1 plus x2 plus xn by n. The expected value of x bar is what? It is expected value of this whole thing, x1 plus x2 plus xn by n. And you know this relation, if you have expected value of ax plus b, where a and b are constant, what is this equal to?
A into expectation of x plus b.
Yes, a into expectation of x plus b. So there is this linearity of expectation. So if you apply that, then you get 1 by n multiplied with expectation of x1 plus expectation of x2 plus expectation of xn. Each of these is equal to mu. So this is mu, this is mu, this is mu. So you get 1 by n into mu is equal to mu. So you get that expected value of x bar is equal to mu. Okay. And then similarly, we will now show for variance. So the proof for variance is also straightforward. So what is variance of ax plus b?
A square.
Yes. So it is a square into not complicate, into variance of x. So b has no role to play. So in this, so when we want to compute variance of x bar, that is variance of x1 plus x2 plus xn by n. Now the point here is they are independent. Xi are independent. This is important. We said that in the beginning when we were defining the over here. So we said that here. X1 to xn are independent random variables. So we said that they are independent. So xi are independent. So what does this mean? That means that we can write it as variance of x1 by n plus variance of x2 by n plus variance of xn by n. 1 by n square comes out. 1 by n square variance of x1 plus variance of xn. Now each of these is equal to sigma square. So this becomes 1 by n square into n into sigma square. So we get it to be equal to sigma square by n. So this completes the proof for the theorem that we had verified using various examples. Okay, so this completes today's lecture. We will have a tutorial with very simple problems. The tutorial is on Thursdays and the tutorial is on Thursdays, but the next lecture is on Friday. So we'll have a short tutorial just to try out some problems and get a hang of the thing. And from next week onwards, it will become slightly more involved. But my invitation is to attend all the tutorials and all the lectures. That is a real practice. Okay. Yeah. Okay. Thank you, guys. Bye bye.
Do we have a lecture on Friday, as like we are moving to the campus on those days, so it won't be possible for all of us to attend the lecture at that time.
So I'm not aware of this part. I have been told that we have lectures. If you want to cancel it, you need to talk to Dean Academics. The information that I have is that from 18 April, we have offline lectures, and till 18 April, we have online lectures. And we have not received any notification that says that there is any particular holiday.
Okay. Thank you.
Okay, so we will have the lecture on Friday, unless there is a notification from Dean Academics to that effect. Okay, guys, bye bye.